Remember when your dad told you about the hottest engines from the 50s? You probably heard stories about big blocks and multiple carburetors, tales of chrome and horsepower that defined an era. But if you thought you knew everything about Chevy's legendary small block, you're in for a surprise. What you didn't know is that in 1957, Chevrolet created something so advanced, so revolutionary, that it changed the automotive world forever. And it came with secrets that even die-hard gearheads don't know. In the next few minutes, you'll discover 20 weird facts about the 1957 Chevrolet 283 fuel-injected engine that will blow your mind, including one fact that's so bizarre, it involves a space program and a future that never happened. The ramjet fuel injection was more expensive than the entire base car. Here's something that'll make your jaw drop. The Rochester ramjet fuel injection system cost $800 as an option in 1957. Now that might not sound like much today, but consider this. A base Chevrolet 152-door sedan cost just $2,048. That means the fuel injection alone was nearly 40% of the entire car's price. It was like buying a Chevy and then paying almost half that amount again just for the engine upgrade. The system was so expensive because it was essentially aerospace technology adapted for automotive use. Each unit was hand-assembled and calibrated, requiring skilled technicians who understood the complex relationship between fuel pressure, manifold vacuum, and throttle position. The main fuel meter alone had over 60 precision machine parts, each one critical to proper operation. Many dealers actually tried to talk customers out of ordering fuel injection because they were terrified of having to service it. In fact, some Chevy dealers in rural areas flat out refused to sell fuel-injected cars, knowing they didn't have anyone on staff who could work on them. The real kicker? For that astronomical price, you got an engine rated at 283 horsepower, exactly 1 horsepower per cubic inch. While that was certainly impressive for 1957, you could get a dual quad carbureted version making 270 horsepower for just half the price. But the fuel injection wasn't really about raw power. It was about Chevrolet proving they could out-engineer anyone, including the Europeans who had been experimenting with fuel injection since before World War II. If you thought that was impressive, wait until you see what's coming up. A fuel injection system that could think for itself, the surprising connection to America's space program, and a secret testing facility that Chevrolet never wanted the public to know about. So let's continue. It was secretly developed in a converted pickle factory. The birthplace of Chevrolet's revolutionary fuel injection system wasn't some high-tech laboratory or gleaming research facility. It was actually developed in a converted pickle factory in Rochester, New York. Rochester Products Division, which was part of General Motors, had taken over the old Beech-Nut pickle plant in 1954 and transformed it into their secret fuel injection development center. The building still reeked of vinegar and brine when the engineers first moved in. They had to work around massive pickle vats that were too expensive to remove, using them as storage for prototype parts. The irony wasn't lost on anyone. Here they were developing space-age technology in a building that had spent decades making pickles and sauerkraut. Engineers would joke about their pickle-powered fuel injection, but the location was actually chosen for its secrecy. Nobody would suspect that cutting-edge automotive technology was being developed in an old food processing plant. The pickle factory location also provided unexpected benefits. The building's thick walls, designed to maintain consistent temperatures for food processing, proved perfect for the precision testing required for fuel injection calibration. The old brine storage tanks were converted into fuel testing reservoirs, and the refrigeration systems originally used for pickle storage were repurposed to test cold weather starting characteristics. Even more bizarre, some of the stainless steel tubing from the pickle production lines was actually used in early prototype fuel injection systems. So in a very real sense, your 1957 fuel-injected Corvette had DNA from the pickle industry. John Dolza was obsessed with toilets before fuel injection. The mastermind behind Chevrolet's fuel injection system had one of the strangest career paths in automotive history. John Dolza, the brilliant engineer who designed the ramjet system, spent years before joining GM working on, wait for it, toilet flush mechanisms. He held several patents for improved toilet valve designs and was considered one of America's foremost experts on fluid dynamics in bathroom fixtures. This bizarre background actually made him perfect for designing fuel injection. The principles of controlling water flow in toilets, pressure differentials, valve timing, and preventing backflow translated directly to controlling fuel flow in engines. Dolza often explained fuel injection to confused executives by comparing it to toilet operation. Think of it as a very precise toilet that flushes gasoline instead of water, he once famously said in a board meeting, causing several GM executives to nearly choke on their coffee. His toilet expertise showed up in unexpected ways throughout the fuel injection design. The main fuel control valve used a float mechanism remarkably similar to a toilet tank float. The vacuum-controlled enrichment system worked on principles Dolza had developed for water-saving toilet designs. He even insisted on using vitreous china insulators in some prototype components because of his experience with ceramic materials and plumbing fixtures. When the fuel injection system was unveiled, one automotive journalist who knew about Dolza's background quipped that Chevrolet had finally built an engine that could flush the competition. The system could learn your driving habits. Here's something that sounds like it came from a modern car, but it was actually true in 1957. The Rochester fuel injection system had a primitive form of adaptive learning that would adjust to your driving style. This wasn't computer, used what engineers called mechanical memory through a series of specially designed springs and linkages that would gradually change their characteristics based on how the car was driven. If you were a lead foot who constantly mashed the throttle, the fuel enrichment circuit would slowly adjust to provide slightly more fuel during acceleration. If you were a gentle driver, the system would lean out over time to improve fuel economy. This happened through metal fatigue and carefully designed components that were meant to wear in rather than wear out. The process took about 2,000 miles to fully adapt to a driver's habits. Mechanics were instructed never to replace certain springs and linkages during the break-in period because they were still learning. This caused huge problems in the used car market because a fuel-injected car that had adapted to one driver would run poorly when sold to someone with completely different driving habits. Some dealers actually had to keep fuel-injected cars for several weeks after trade-in, having different employees drive them to reset the mechanical memory before reselling them. It was so advanced that even GM's own engineers didn't fully understand all the ways the system adapted until years after production ended. The fuel injection unit was worth more than gold. In 1957, the complete Rochester fuel injection unit literally contained more value per pound than gold. This wasn't hyperbole, it was mathematical fact. The entire system weighed about 35 pounds and cost $800, which worked out to about $23 per pound. Gold in 1957 was selling for $35 per ounce, or $560 per pound. While the fuel injection wasn't quite worth its weight in gold, when you factored in the precision machining and assembly time, economists calculated that the manufacturing value added to the raw materials made each unit worth approximately $600 per pound in 1957 dollars. This incredible value made fuel injection units prime targets for thieves. Several Corvettes had their fuel injection system stolen right out of the engine bay while parked. The units were small enough to carry and valuable enough to make the risk worthwhile. Some owners actually installed hidden locks and chains to secure their fuel injection systems, similar to how people today might secure expensive wheels. Insurance companies initially refused to cover fuel injection as standard equipment, classifying it as a special accessory that required additional premiums. The black market for stolen fuel injection units became so problematic that GM started stamping hidden serial numbers in multiple locations on each unit. They also created a registry to track every fuel injection system by serial number, making it one of the first automotive components to have comprehensive theft tracking. Some racers who couldn't afford new units would buy stolen ones, no questions asked, creating an underground economy that GM tried desperately to shut down. It was banned from NASCAR after just 3 races. The fuel-injected 283 was so dominant in its brief NASCAR appearance that it was immediately banned. In early 1957, a few brave teams showed up with fuel-injected Chevrolets, and the results were devastating for the competition. The fuel injection's ability to maintain perfect mixture through high-speed turns gave it a massive advantage over carbureted engines that would stumble or go rich in the corners. At Daytona's beach course, Buck Baker's fuel-injected Chevy lapped the entire field twice, something that had never happened before in NASCAR history. The fuel injection system's consistent power delivery allowed drivers to stay on the throttle longer through turns and accelerate earlier coming out. Bill France, NASCAR's founder, watched in horror as traditional carbureted cars were made to look obsolete. After just 3 races, he called an emergency meeting and banned fuel injection, claiming it was too expensive for the average racer and would ruin the sport. The real reason for the ban was pure politics. Ford and Chrysler executives had privately threatened to pull out of NASCAR entirely if fuel injection was allowed to continue. They were at least 2 years behind GM in fuel injection development and couldn't compete. The ban stood for decades, and some historians argue it set American fuel injection technology back by 20 years. Ironically, many of the banned NASCAR fuel injection units ended up in drag racing, where they dominated for years until rules caught up there too. The air meter was designed by a musician. One of the most critical components of the ramjet fuel injection was its air meter, and bizarrely, it was designed by a part-time jazz saxophone player named Eugene Wall. Wall wasn't even an automotive engineer. He was a GM accountant who played sax in Detroit jazz clubs on weekends. He got involved in the fuel injection project by accident when he mentioned to his boss that the airflow in a saxophone could be measured the same way as airflow in an engine. His musical background gave him unique insights into airflow dynamics. He understood how small changes in air velocity could create huge differences in pressure, just like in a saxophone's tone holes. Wall designed the air meter using principles he learned from studying how jazz musicians could bend notes by changing their embouchure. The final design used a Venturi effect that was remarkably similar to how a saxophone mouthpiece works, creating precise pressure drops that could be measured and converted to fuel flow requirements. The air meter was so sensitive it could detect the difference in airflow caused by a dirty air filter after just 100 miles of driving. Wall's musical approach to engineering was so successful that GM hired several more musicians for their research departments, believing that musical training provided unique insights into fluid dynamics and harmonics. Wall himself continued playing jazz throughout his career, often joking that the fuel-injected 283 was the only engine that could play the blues. Corvette fuel injection was almost exclusive to hearses. This sounds completely insane, but it's true. Chevrolet initially planned to make fuel injection exclusive to Corvettes and funeral cars. The logic was actually sound, if morbid. Funeral directors had been complaining for years about carbureted engines stalling during slow funeral processions. The constant low-speed operation and frequent stops wreaked havoc on carburetors, leading to embarrassing stalls during solemn occasions. GM executives saw fuel injection as the perfect solution for hearses. The system's ability to maintain perfect idle and low-speed operation would eliminate funeral procession stalls. They even developed a special funeral mode calibration that prioritized smooth idle over performance. Several prototype fuel-injected hearses were built by GM's Special Vehicles division, and they performed flawlessly in testing. Funeral directors who tested them were amazed at how smooth and quiet they were during processions. The plan fell apart when Corvette chief engineer Zora Arkus Duntov found out about it. He was furious that his high-performance fuel injection system might be associated with funeral cars and threatened to quit if the plan went forward. The internal battle was so heated that it reached GM's board of directors. In the end, Duntov won, and fuel injection remained a Corvette exclusive for 1957, though a few funeral car builders did manage to special order fuel injection units through back channels. These funeral spec units are now among the rarest and most valuable fuel injection systems ever made. The system used spider silk. In early prototypes during development, engineers faced a critical problem measuring minute fuel flow rates. Traditional flow meters were too crude for the precision required. The solution came from an unexpected source: spider silk. Dr. Helen Cartwright, one of the few female engineers at GM in the 50s, suggested using spider silk as flow indicators after reading about its use in World War II bomb sites. The team actually hired a spider wrangler who maintained colonies of orb weaver spiders specifically for harvesting silk. The silk strands were stretched across clear tubes in the fuel system, and their deflection under flow was measured with microscopes. Spider silk was perfect because it was incredibly strong, didn't absorb fuel, and would deflect predictably based on flow rates. Each test unit required about 50 feet of spider silk, carefully harvested and installed by technicians wearing jeweler's loops. This bizarre testing method was kept secret for decades because GM executives thought it sounded too strange for public consumption. They were probably right. Imagine trying to explain to customers that their high-tech fuel injection was developed using spider webs. The spider silk testing revealed flow patterns that conventional instruments missed, leading to several crucial design improvements. When synthetic materials finally replaced spider silk, the test results were never quite as accurate. Some veteran engineers kept using spider silk for special projects well into the 60s, maintaining their own personal spider colonies in GM labs. It could run on perfume in emergencies. The Rochester fuel injection system had an astounding characteristic discovered by accident. It could run on high-alcohol perfumes in an emergency. This was discovered when a GM executive's wife accidentally put her purse containing a broken perfume bottle on a test engine. The perfume leaked into the fuel injection test tank, and to everyone's amazement, the engine kept running, though it smelled like a department store. Engineers investigated and found that any liquid with more than 70% alcohol content could keep the engine running through the fuel injection system. This included perfumes, colognes, and even some medicines. The fuel injection's precise metering could compensate for the different combustion characteristics of these alternatives, though power was reduced by about 40%. This capability was actually documented in military versions of the system as an emergency fuel alternative. The perfume compatibility led to one of the strangest promotional events in automotive history. At the 1957 Paris Auto Show, Chevrolet demonstrated a fuel-injected Corvette running entirely on Chanel No. 5. The stunt was meant to show the system's sophistication to European audiences who were skeptical of American technology. The demonstration worked perfectly, though the exhaust smell reportedly made several attendees feel faint. The French press was so impressed that they called it le moteur parfumé, the perfumed engine. Coco Chanel herself was said to be amused and sent a case of perfume to GM's president with a note saying, "For your next demonstration." The fuel pump was tested with peanut butter. The high-pressure fuel pump was one of the most critical components, and it underwent one of the strangest testing procedures in automotive history. Engineers needed to test the pump's ability to handle thick, viscous fluids under extreme conditions, simulating worst-case scenarios with contaminated fuel. After trying various test fluids, they settled on creamy peanut butter as the perfect testing medium. The peanut butter tests were conducted in a special lab that GM employees nicknamed the Sandwich Shop. Technicians would fill the fuel system with Skippy Creamy, smooth consistency was crucial, and run the pumps continuously for hours. If a pump could circulate peanut butter for 24 hours without failing, it was deemed strong enough for any real-world condition. The test consumed about 50 jars of peanut butter per week, leading to GM purchasing peanut butter by the pallet. This unusual testing method actually revealed several design flaws that normal testing missed. The peanut butter's consistency exposed weak spots in pump seals and showed how the pump would perform with heavily contaminated or gelled fuel. Some pumps that passed all conventional tests failed miserably with peanut butter. The testing was so effective that it continued even after production began. Legend has it that failed test pumps were cleaned and donated to local schools, where janitors wondered why their peanut butter sandwiches tasted faintly of gasoline. Have you ever wondered what other bizarre testing methods Detroit used in the 50s? Let me know in the comments if you've heard any strange stories about classic car development. The CIA bought dozens for secret projects. Here's a fact that remained classified for decades. The Central Intelligence Agency was one of the biggest customers for fuel-injected 283 engines in 1957 and 58. They didn't put them in cars, though. The CIA's Technical Services Division saw the fuel injection system as perfect for various covert devices and ordered complete units directly from GM through classified contracts. The agency was particularly interested in the fuel injection's precise metering capabilities. They modified the units to disperse everything from tracking powders to chemical agents. Some units were converted into high-pressure spray systems for marking money or documents with invisible compounds. Others were adapted as precision fuel systems for experimental aircraft and boats. The mechanical computer aspects of the fuel injection were studied for possible code-breaking applications. One declassified document mentions a Project Rainbow that used fuel injection components in some kind of communications device. The strangest CIA application was using the fuel injection's vacuum sensing system as part of an altitude measuring device for spy balloons. The system's ability to compensate for altitude changes in automobiles translated perfectly to measuring atmospheric pressure at high altitudes. These modified units were so sensitive they could detect altitude changes of less than 10 feet. When Gary Powers' U-2 spy plane was shot down in 1960, investigators found components that looked suspiciously similar to Rochester fuel injection parts in the wreckage, though the CIA never confirmed the connection. It caused Corvettes to catch fire at stoplights. The fuel injection system had a terrifying flaw that GM desperately tried to hide. Under certain conditions, it could cause engine fires at stoplights. The problem occurred when the engine was hot and suddenly shut off, like at a traffic light. Residual fuel pressure combined with engine heat could cause fuel to vaporize in the lines and spray onto hot exhaust manifolds when restarted. The first reported fire happened in Detroit when a GM executive's wife stopped at a light in a fuel-injected Corvette. When she restarted the engine, flames shot out from under the hood. She escaped unharmed, but the car was totaled. GM initially blamed it on a mechanic's error, but when more fires occurred, they realized it was a design flaw. The fires were especially common in hot weather and in stop-and-go traffic. GM's solution was typically 1950s. They created a secret fire suppression kit that dealers installed without telling customers what it was for. The kit included heat shields, rerouted fuel lines, and special insulation. Dealers were instructed to install it during routine service and bill GM directly using a code that didn't appear on customer invoices. When customers asked what the new parts were, dealers were told to say they were performance improvements. The cover-up worked so well that most 1957 fuel injection owners never knew their cars had been retrofitted to prevent fires. Today, these fire suppression kits are rare and valuable, as many were removed by later owners who didn't understand their purpose. The Soviets tried to copy it and failed spectacularly. In one of the Cold War's stranger episodes, Soviet spies managed to steal complete blueprints for the Rochester fuel injection system in 1958. The KGB operation, codenamed Operation Carburetor, showing how little they understood the technology, successfully photographed thousands of pages of technical documents and even acquired several complete units through shell companies. The Soviets assigned their best engineers at ZIL, Zavod imeni Likhachova, to reverse engineer the system for use in government limousines. What followed was a comedy of errors that would have been funny if it hadn't wasted millions of rubles. Soviet manufacturing couldn't achieve the precision tolerances required. Their best machining was still too crude for the fuel injection's tiny passages and precise clearances. They tried making parts larger to compensate, but that threw off all the calculations. The Soviet copy, designated the R-58 system, was installed in exactly 3 ZIL limousines before the project was abandoned. All 3 cars suffered catastrophic failures within days. One caught fire during a parade, ironically validating GM's fire concerns. Another hydro-locked its engine when the fuel control went haywire, and the third simply refused to start after the first day. Soviet engineers concluded that American fuel injection was capitalist witchcraft and went back to carburetors. Pieces of these failed Soviet fuel injection systems occasionally surface in Eastern European scrap yards, recognizable by their Cyrillic casting marks and comically oversized components. Early units used actual gold in the fuel distributor. The first 100 pre-production fuel injection units contained more gold than a jewelry store. Literally. Engineers discovered that gold's corrosion resistance and malleability made it perfect for crucial fuel metering surfaces. Each early unit contained about 2 ounces of gold plating in the fuel distributor, worth more than $70 in 1957 money. The gold-plated components were primarily in the fuel metering valve seats and the main distribution spider. Gold's properties allowed for incredibly precise fuel metering and prevented any corrosion that could alter flow rates. The gold surfaces were so smooth that fuel would bead up like water on wax. This level of precision was impossible with conventional materials, making gold essential for meeting performance targets. GM executives nearly had heart attacks when they saw the cost projections for production units with gold components. A frantic search for alternatives began, eventually leading to special hardened steel alloys that could match gold's performance. However, the first 50 production Corvettes with fuel injection actually did have gold-plated components, making them incredibly valuable today. Most owners don't even know they have gold in their fuel injection systems because GM never publicized it. A few restoration specialists have discovered the gold plating when disassembling early units, often thinking it was aftermarket modification until they researched the date codes. It was originally designed for aircraft. The ramjet fuel injection wasn't originally intended for cars at all. It was developed for aircraft that never made it to production. In 1953, GM's Allison division was working on a light aircraft engine for private planes. They needed fuel injection because carburetors had altitude compensation problems. When the aircraft project was canceled, the fuel injection development was transferred to the automotive division. This aircraft heritage showed in many design features. The system could automatically compensate for altitude changes up to 15,000 feet, completely unnecessary for cars but essential for aircraft. The fuel pump was designed to prevent vapor lock at high altitudes where fuel could boil. The entire system could operate inverted or at extreme angles, anticipating aerobatic maneuvers. Even the mounting brackets were designed to withstand G-forces far beyond what any car would experience. The aircraft DNA created some amusing situations in automotive use. Mechanics were baffled by features that made no sense in a car, like drain valves positioned for inverted flight or pressure relief systems designed for rapid altitude changes. The owner's manual actually contained warnings about operating above 10,000 feet elevation, leading some Colorado Corvette owners to worry unnecessarily. The system's ability to run at any angle did prove useful for one unexpected application. Off-road racers discovered that fuel-injected engines would keep running during extreme hill climbs or rollovers when carbureted engines would stall. The assembly line workers were sworn to secrecy. GM treated fuel injection assembly like a military secret. Workers at the Rochester plant had to sign confidentiality agreements and submit to background checks, unprecedented for automotive manufacturing in the 50s. They weren't allowed to discuss their work with family or friends, leading to the facility being nicknamed Area 57 by locals. The secrecy was partly justified. Industrial espionage was rampant, and Ford had already been caught trying to infiltrate the facility. Workers entered through a special entrance and weren't allowed to bring cameras or even paper and pencils onto the floor. Their uniforms had no pockets to prevent them from smuggling out parts or documents. Lunchboxes were searched daily, and workers ate in a segregated cafeteria where they couldn't mingle with employees from other divisions. The paranoia reached absurd levels. Workers were forbidden from drawing fuel injection components, even as doodles. One assembler was fired for sketching a fuel distributor on a napkin during lunch. Another was investigated by GM security for mentioning injection in a letter to his mother. He was talking about a medical injection, but the mail sensors didn't care. The security measures were so strict that when production ended, many workers had to be deprogrammed before returning to regular automotive work. Some veterans of the fuel injection line said it was more like working at a weapons plant than a car factory. You could order secret racing calibrations from dealers. While GM publicly denied it, select dealers could order special off-road only fuel injection calibrations that dramatically increased power. These weren't advertised and required knowing the right code words. Customers would ask for special application tuning or high-altitude calibration, and knowledgeable dealers would order units with radical cam timing and fuel curves. These racing calibrations came in 3 levels, internally known as mild, wild, and insane. The mild setup added about 15 horsepower with aggressive fuel curves and advanced timing. The wild calibration required aviation fuel and added 30 horsepower, but would destroy the engine if run on pump gas. The insane calibration was essentially a drag racing setup that required alcohol fuel and would only last a few runs before rebuilding. Each special calibration cost an extra $200 and came with paperwork stating it was for marine use only to avoid liability. The existence of these factory hot rod parts was an open secret in racing circles, but officially denied by GM until the 1990s. Dealers who sold too many would receive threatening letters from GM Legal, but the profits were too good to resist. Some dealers became famous for their willingness to provide racing calibrations, with customers driving hundreds of miles to buy from them. Today, original racing calibration units are the holy grail for collectors, with documented examples selling for more than complete cars. The fuel injection computer was mechanical. The most mind-blowing aspect of the 1957 fuel injection was its mechanical computer that calculated fuel requirements without a single electronic component. This analog computer used a series of cams, springs, levers, and diaphragms to perform calculations that wouldn't be done electronically until the 1980s. The system continuously solved complex equations involving air temperature, pressure, flow rate, engine speed, and throttle position. It did this through mechanical integration, using the physical movement and interaction of components to perform mathematical operations. The main control unit contained over 200 precision parts that moved in concert to determine exact fuel requirements thousands of times per second. It was essentially a mechanical artificial intelligence that could adapt to changing conditions instantly. The complexity was staggering. One GM engineer calculated that the mechanical computer performed the equivalent of about 50 mathematical operations per engine revolution. At 6,000 RPM, that meant 5,000 calculations per second, all done with springs and levers. The system was so sophisticated that when GM finally developed electronic fuel injection in the 80s, they used the mechanical system's algorithms as the basis for the computer programming. Some engineers argued that the mechanical system was actually more reliable than early electronic versions because it couldn't suffer from electrical failures or require software updates, is responsible for the moon landing. This sounds like an outrageous claim, but the 1957 fuel injection system directly contributed to the Apollo moon missions. Several key NASA engineers who worked on the Saturn V rocket's fuel system were veterans of GM's fuel injection program. They applied lessons learned from the ramjet system to solve critical problems in rocket engine design. Tom Mueller, who later became SpaceX's founding propulsion engineer, started his career working on Rochester fuel injection. He often credited the mechanical fuel control system with teaching him fundamental principles that he applied to rocket engines. The concept of pressure-driven fuel metering without pumps, pioneered in the ramjet system, was adapted for spacecraft attitude control thrusters. The mechanical computer's ability to maintain precise fuel-air ratios inspired similar systems for controlling rocket fuel mixture ratios. The most direct connection came through the Saturn V's gas generator, which used principles directly lifted from the 1957 fuel injection. The way it metered fuel to create hot gas for drive and turbopumps was essentially a scaled-up version of the Rochester system. When Neil Armstrong stepped onto the moon, he was aided by technology that started in a converted pickle factory in Rochester, developed for a 283 cubic inch V8. Several NASA old-timers kept fuel-injected Corvettes as personal cars, calling them baby rocket ships and meaning it more literally than anyone knew. That's all for today, folks. If you enjoyed this video, don't forget to subscribe and hit that like button so you don't miss the next one. See you there.